Mr. Humbard here. Let's go through part 2 of this video on 3.2 equation derivations. Alright. So to start this time around, we're going to cover the second row, the distance equation where acceleration is not given. So the way to think about this is before we did the graph of velocity versus time. Now we're going to do the position versus time graph. And if you are accelerating, we know that it's not going to be a straight line anymore like it was before. So let's discuss both versions. So this is we'll say it's an xt plot. We know from before that this would be x initial, that would be x final up here, and where you're at in the graph, this will be the final, this would be the initial, and that's this distance. The blue one is from this one down to that origin, and the rise over the run, of course, is the rise in the y. Your slope's going to be this x final minus x initial, and that distance of time, that time period. And we know that the slope of a position versus time graph is velocity, so our equation looks like this. Equals x v, here we write that. Like so. Which is very similar to y equals mx plus b. This time around though, it's going to be a little different. So what if, I'll write it over here, we're accelerating. We know that now our velocity versus time plot looks like what we have here, and not our position versus time plot. Our position versus time plot, like we saw on the ball drop lab, looks like a quadratic. If next accelerating, it's going to be upward. This is our x, and this is our t plot. For this one though, what you can think of to solve this is zoom in on a very small section of the graph. If we make this really, really tiny, like say here, that's pretty much a straight line. A little more, it's approximately a straight line. A little bit more, it's still kind of a straight line. A little bit further, it kind of stops being a straight line after that point. So if we kind of zoom in on that, and we can do from some time period, make a pretty good approximation that if we are at some time period here, and we go forward a little bit here, we're mostly at a straight line, and we're going to have some initial position over time slope, and then a final position over time slope, which we can kind of average out. So our velocity here for this equation changes to an average, and we know an average is just the v average is just some final velocity plus some initial velocity divided by 2. Because to average numbers, you add the numbers up by the number of numbers and you divide by that total. So that is what we're going to change this to. And now we just plug that in for right here. So our equation changes a little bit, but not too much. In the case of constant acceleration. And we have v final plus v initial 1/2, and this is going to be plus x initial. So if I subtract x initial to both sides, I will get some change in x equaling, oh, and I'm missing a t there, aren't I? Here. There we go. 1/2 v final plus v initial time. And this is one of our equations we can use. And that t was from this one over here. So that is one of the equations. And of course, there's variations of this equation, so we can find those as well. So when acceleration is not given, we can use this form equals v initial plus v final t2, and it really is just the average that's here. So everything else is the same mostly as the first row, and this time around you just have this quantity that you can break up as needed. That's why it looks a little different. So if we want time, we divide by the reciprocal of that. So whatever this is, inversed, I multiply that to both sides, which is just going to be 2 over vi plus vf. All right, so that will give us my time equation. So 2 delta x over vi plus vf, or vf plus vi on the bottom, doesn't matter. So there's another one. And then for the others, I'm going to have to divide away the t instead. So let me write out this one again. So t is multiplied here. I'm going to have to change this so that the 2 is underneath the t. I'm going to have to multiply this by 2 over t. So once I do that, I'm going to get this will cancel nicely, that will cancel nicely. 2 change in x over time equaling v initial plus v final. And then I just have to decide which one I want. If I want v final, v initial goes on the left and is negative. Or right, as it were. If I change that around by subtracting vi both sides. So that's another one. And if I want v final or v initial, I just have to subtract v final. Right, so now I get v initial equals 2 change in x over time minus my v final. There's another equation I've solved for. And our initial one, I'll have to put, I'll just circle it right here. we go. So that should be everything.